more or less joined. Yeah. So on the request of some students, I will start with a quick recap of a couple of questions we did in the end last time. So we'll discuss them again. So this is our second session of relative motion, part of the kinematic series. Okay, so we'll quickly take a recap of the example from the last particular thing we did, question we did in the previous lecture. So just go through your notes from that previous lecture and see it, you'll understand. Okay. Okay, so the example was something like this. You had two objects moving in the same direction. Still have some late joinings, okay. And one in the opposite direction. So this was A and this was B. And this was C. Now each of them were moving with constant velocities. VA, VB and VC. So we'll take some arbitrary values today just to understand the concept of the question again. So A and B are moving along this side of the road, along a straight road, and C was moving in the opposite direction of the straight road. Okay. And initially the distance was D like this between them. So we had equal gaps. These gaps were equal. So anyway, so suppose at time t equal to 0, both these are 50 meters each, okay, and A, B and C are moving at uniform velocities. VA is equal to, let's say, 20 meters per second. VB is 25 meters per second. And VC is suppose something again, let's say 10 meters per second. So we have to find, first of all, velocity of B with respect to A and velocity of C with respect to A. So this was the notation. This thing would be the relative velocity of B with respect to A. This was the notation we used, that when we write B comma A, it is of B with respect to A. Similarly, this one would be relative velocity of C with respect to A. So keeping that notation in mind, calculate this. Okay. Then we have to find the time, let's say T1, at which C and A cross each other, and the distance between A and B at this instant of time. And likewise, we have to also find, yes, correct. Bhaumik, your answers are correct. Okay. So the time T2 at which B is about to overtake A, and the distance between C and A at this instant. Okay. So it's exactly the same question, though the data is different. Okay. But the concept of the question is just the same. So it will just give you an idea about how we solved it. So if you have the lecture notes with you right now from the previous lecture, I'd like you to go through that solution of the last question we did last time and try this question out yourself. Okay. Give me the answers of the first and second part to begin with. Yes, Aparna, to answer your question, relative motion will be there in the test coming up. Albeit simple example of relative motion, the type we have done in the last lecture, where there is no acceleration involved. Today's lecture, we will also see relative acceleration, but in the last week's lecture, we had seen up to this thing, up to relative motion with velocity only, with zero acceleration, relative motion with uniform velocity, the type we are seeing over here. So up to that thing you can be asked. Yes, Dhruv, your answer is correct. Yuvraj, I will send you some tips with the doubts that you sent me on WhatsApp separately. Okay, because yes, that's correct. Dhruv, the second part is also correct. So your answers to the first question should be this, that if you strictly take in terms of direction also, if you take this direction as positive and this opposite direction as negative, then we can write the velocity of A with proper sign as plus 20, velocity of B with proper sign as plus 25, and the velocity of C with proper sign as minus 10, okay, in meters per second. So for example, the velocity of B with respect to A will be velocity of B minus velocity of A. So it will become plus 5 meters per second. Okay. Velocity of C with respect to A will be velocity of C minus velocity of A. So with proper sign, that will become minus 30 meters per second. Okay. If you're just giving the magnitude, then it's okay to say it's 5 and 30. But if you're giving with the direction also, then this is the proper answer with the algebraic sign. C and A are going in opposite directions, so the magnitude of the speed will be more. It will not be the difference, it will become the sum. So A is going with the speed of 20 and C is coming in the opposite direction with the speed of 10. So to A, it will look like C is going faster actually. That's why it will become 30 meters per second in magnitude. Okay, Aparna, I hope that is clear to you. Okay, good. So now let us understand the second part. So for the second part, since we have already calculated the motion relative to E for B and C, let us do that. Let's solve the motion. So the motion of B and C as seen relative to A. So basically, if you're sitting inside the car of A, if our observer is here inside the car A, then to him or her, what does the motion of B and C look like? Let's understand that. So B is, let's say, over here at time t equal to 0. Okay. So B is behind at a distance of 50 meters. But more importantly, B is traveling with a relative velocity in this direction. So it's plus 5. So it's this direction. Whereas on the other hand, C is at that moment somewhere here. And to A, it is looking like C is traveling in the negative direction. So the arrow is pointing like this with a magnitude of velocity of 30 meters per second. Here I don't need to put the minus sign because I'm already showing the direction by an arrow. Okay, so that is sufficiently done. So since I'm showing that, specifying the direction of motion with an arrow, so it's fine. So this is where C is located at time t equal to 0. So to this observer, it will look like C is coming closer from this direction and B is coming closer from this direction, and of course this distance is also initially 50 meters. Okay. Remember, I told you that the car's own size is negligible compared to this 50 meters and all. Okay. So now after some time, suppose we observe that C reaches somewhere here. Okay. Now we observe that C has reached this position. Somewhere here like this. At some new time, t equal to t1. So the thing is, how do we calculate this time t1? So you can see that in A's frame, C is displaced by how much? C is displaced by 50 meters. And during that time, B would have displaced by a lesser amount because B's speed is less. Okay. So this is where B would be at t1. So you can see in this diagram, okay, if I just miniaturize this a little bit more, okay. So it's like you are sitting on A. So to you, A is looking stationary. B started from here at t equal to 0, and C started from here at time t equal to 0 with these kind of velocities. This was moving in your frame at 5 meters per second. This was moving in your frame at 30 meters per second, like this. And these distances were 50 meters each. Okay. Now imagine the instant when A and C are crossing each other. So what has happened to, from the point of view of this observer who's sitting inside the car A, for him the car A is not moved, no? Because he's sitting inside the car A. So for him A has remained where it is, but C has moved all the way from here and just come alongside him here. At that time t1, which we want to calculate, C has moved here. Whereas in that same amount of time, B would have moved and reached somewhere over here. So we want to find out this distance. So it's some d prime now. We want to find out that distance. Okay. So you can see that from t equal to 0 to t1, okay, the displacement of C with respect to A is actually backwards. So it is minus 50 meters. Okay. Or you can say 50 meters towards E. Okay. And during that time, the velocity of C with respect to A was minus 30 meters per second. So that was basically a speed of 30 meters per second towards E. That is what you're seeing in the arrow. This relative velocity is towards E, 30 meters per second like this. Okay. So we can, and acceleration is 0 over here. So we can see that therefore time t1 is just that, that distance of 50 meters at that speed of 30 meters per second. So that is equal to 1.67 approximately, or more accurately 5 by 3 seconds. Okay. That's the thing. Okay, now during the same time, what is happening is that B is maintaining a constant speed with respect to A of plus 5 meters per second. So what should be B's displacement with respect to A? It should be 5 meters per second into that time t1. So it should be 5 into 5 by 3. 25 by 3, or approximately 8.33 meters. This should be B's displacement towards E. So that means in that time 0 to T1, B moves closer to E by a distance of that much, 8.33 meters. Okay. So therefore A's new distance will be the original distance minus the displacement that B has made towards A. So the original distance was 50 meters. So minus 8.33. Okay. So this will become 41.67 meters. So that will be the distance at which this will be. Okay, so going back to that diagram. So in this diagram now you can see that this distance that B has moved towards E, this one, this is basically how much this is equal to the displacement of B towards E. So that is that velocity of B towards E into time t1. So that is 5t1, or it worked out to be 25 by 3 meters. So here to here, this is 25 by 3. And this d prime we wanted to calculate. So d prime is becoming this whole distance 50 minus this. Okay. So this is how the motion looks with respect to E during that interval of time from 0 to t1, where t1 is that instant of time when C and A are crossing each other. Okay, so just make a note of this diagram and understand this properly. Then we'll also see this by another method. Yes, I'm coming to the last part. Okay. So this is what is happening between A and B. And this is what is happening between B and C. So first you make sure that you understand this one. That during that time 0 to T1, what has happened is C has started from 50 meters ahead and come alongside E. So C का displacement कितना होना चाहिए with proper sign minus 50 with a velocity of how much? Minus 30 meters per second, as seen by the occupant of car E. The person who is sitting inside car A, to him it looks like C has moved the full 50 meters towards him, and C was coming at a speed of 30 meters per second. So obviously in time 5 by 3 seconds is moved 50 meters like this. Okay. But during that same time, if he turns back and looks what B is doing, now during that time 0 to T1, this part, now B's velocity with respect to A, that is plus 5. So again, to the observer sitting inside the car E, it looks like B is coming from behind like this with a velocity of 5 meters per second. and this is where it was at t equal to 0. So at that time t1 it will be somewhere over here. Okay. So now we want to calculate that how much is this distance. This is our d prime. So ये निकालना है, whereas this distance was 50 meters. Okay. So that is this calculation. Okay, so can you now solve the last part using this method yourself? Try to solve the third part yourself. Okay, so I'm putting up the third part over here as you are understanding this also. The third part is you have to find the time, let's say t2, at which B is about to overtake E. Okay. And the distance between C and E at that moment. The distance between A and C at that instant. Just try working this out yourself. Yes, very good. Yeah, Yuvraj, in this question, we are not considering the lengths of the cars. We have already said that it's negligible compared to the distances involved. We'll do another question where we consider the length of a longer object, like a train or something. Okay, so let's come to this third part now. So in the third part, you again rewind to t equal to 0. Okay. When our observer is inside the car A, okay, and the car B is somewhere behind here at a distance of 50 meters. Now, and of course, is moving with a velocity relative to A of 5 meters per second. So now the question is, when does he, move enough that he's now somewhere here and just about ready to go around like this overtake. Okay, so that happens. Let's say he's just reached alongside. Just about ready to overtake now. So this has happened at some time t2. So during that time, how much B is displaced? B is displaced 50 meters in A sprint. So the displacement of B with respect to A in that time is 50 meters. Okay. So from T equal to 0 to T2, the velocity of B with respect to A is constant at plus 5 meters per second. But the displacement of B with respect to A is supposed to be 50 meters, plus 50 meters. So therefore the time T2 is just the ratio of that distance to uniform relative speed. So 10 seconds. So this is happening at 10 seconds. Okay. And now during those 10 seconds, we want to also observe what has happened to C. So at the beginning of all this, C was somewhere here. So when this motion started at t equal to 0, C was over here, also at 50 meters in front. But remember, C is going much faster. C's velocity is now, with the sign it was minus 30, so as a magnitude it is 30 meters per second relative to A. So in that 10 seconds that B has reached from here to here, C has actually gone past and reached somewhere here. So C would have gone past in 10 seconds and C would now be somewhere here. So this value here would be the displacement of C with respect to A in time 0 to T. So in 0 to T2, which is actually 10 seconds, which we got here, the velocity of C with respect to A with proper sign is minus 30. So the displacement of C with respect to A should be minus 30 meters per second multiplied by the time of 10 seconds. So it should be minus 300 meters. Okay. So now you can see in this diagram, C's initial position at t equal to 0 to C's position now at this time, t equal to t2. ये वाला distance कितना है? ये 300 meters हो गया. So what about this now? This distance, the actual distance between A and C at this point of time, it will become the difference of that and 50. Now with respect to A, you can see C is over here. This is, let's say, D double prime. That is the distance between A's position and C's position at that new time of. Okay, so therefore, the distance between A and C at T2 equal to 10 seconds. That distance, suppose I'm denoting by D double prime, that is becoming 300 meters minus 50 meters, or it is becoming 250 meters. Okay. Yeah, so that is why, Yuvraj, that's what we've done. That's why we have used relative motion over here. That is why in this calculation, the velocity of of B and C that we've considered is with respect to A. We have considered velocity of B with respect to A. We haven't considered velocity of B for this displacement, which is 25 meters. We have considered this because we are solving the motion. We are solving the motion of B relative to A. That is the meaning of relative motion. Relative motion का definition ही वही था. It is motion of one moving body, which in this case is B, relative to, or you can say with respect to, a moving reference frame. Which is A. That is why we are using relative motion over here, because A is also moving, B is also moving. But we want to understand the motion of B as seen by A. No, the question must have been clear, right? It's just a matter of how we solve it. Okay. इसको मैं ground frame से नहीं देख रहा हूँ. Okay. A is not present over here in the ground frame. Actually, A is moved somewhere here, and B is moved somewhere further like that. Okay, now just to explain that concept a little bit further, let us also see what is happening from the ground frame point of view over here. So we have actually completed this question now, but suppose we want to understand the motion of all three, that is E, B and C, as seen in the stationary ground frame. With respect to the stationary frame of the road or the ground, let's say from t equal to 0 to t equal to t2, which was 10 seconds. Let's try to understand how that will look. Okay. So let's try to visualize how the motion would have looked if we were, observing this from the ground, which is stationary. So now for us, A is not becoming stationary. A is also moving, B is also moving, C is also moving. So let's try to understand how that looks. Just excuse me for a moment, guys. Just be back. Okay, so let's understand what the ground frame observer is seeing. What the ground frame observer is seeing is that at t equal to 0, E was, let's say, over here, okay, and moving with a speed of 20 meters per second. Okay. B was, let's say, somewhere over here, at t equal to 0, and moving with a uniform speed of 25 meters per second. And at that same instant, C was somewhere over here, moving backwards like this with a speed of 10 meters per second. Okay. So t equal to 0, this is the case where all these three distances are 50 meters. This is also 50 meters. Remember, we are not taking the size of the car into account. That means we are treating the cars like particles. They're very small in size compared to the distances that we are dealing with. Okay. Now let's just understand what is happening at 10 seconds. 10 seconds में individually उनके displacements कितने होंगे पहले वो लिख लेते हैं. So from 0 to t2 equal to 10 seconds in the ground frame, what will be the displacement of E? It will be velocity of E into time. So that will become 200 meters. Okay. The displacement of B will become velocity into time. So that will become 250 meters. And the displacement of C, if we write with proper sign, it should become minus 100 meters. Okay. So now let's zoom out of this and understand, because we need more space, okay, for this. So let's understand what's happening here. First of all, let's extend these lines a little bit. So we go at my new time, 10 seconds. A would have reached where? A would have reached somewhere which is 200 meters ahead. So if this is only 50 meters, that means A would be somewhere here. This is where A would be. Let's say at the position A prime, which is at T2 equal to 10 seconds. So ये वाला जो distance है यहाँ से यहाँ ये कितना है? This is the displacement of A, which is 200 meters. Okay. Now during that same time, B का displacement कितना हुआ है? 250 meters. So obviously you can see where is B reached. B is actually reached. Okay. B has reached 250 meters from where he started. So B will be here only. So that is why B is just about ready to overtake. Okay, because you can see in this diagram, this whole distance from here to here, this will be B's displacement, जो हमने यहाँ पे calculate किया, 250 meters. So this is how much B has moved. So because B was 50 meters behind, in that much time A has covered 200 meters, B has covered 50 extra meters. That means B is just alongside B. And in that much time, where is C reached? C has reached minus 100 meters. So C has reached somewhere over here. So in fact, interestingly, you see that C would have reached this position because this is 100 meters behind. So C would be here. Let's call this C prime at the time T2 equal to 10 seconds. So this is where C would have reached, and you can see that this distance is what C has traveled. So it should be 100 meters. Okay. So at that moment, you can see what is the distance between A and C. So this is the time. So this is where B is at T2 equal to 10 seconds. So in this diagram, you can now clearly see that as visible from the diagram above, okay, as seen above, at T2 equal to 10 seconds, okay, A and B are alongside each other, and C is at a distance of 250 meters. And that is the information that we had got by solving the relative motion. But see, this is as the observer who's on the ground is seeing this. This is the motion as seen by a guy who's standing stationary alongside the road and observing this. But will the motion look like this for the person who's sitting inside the car? No, because with respect to him, he's sitting inside the car. So A तो वहाँ stationary रह गया. उसको क्या दिख रहा है? उसको जो दिख रहा है, that was in the previous diagram. That C has gone past him and reached 250 meters behind, and B has just come 50 meters in front of him. So imagine what's happening here. A and B are both simultaneously moving. So imagine if you're sitting inside the car A, you're not looking at B moving through a distance of 250 meters. It doesn't look like that to you. It looks like that B has just was 50 meters behind you, and at this time now it is alongside you. So आपको B का motion कैसे दिखेगा? That it's only moved 50 meters. Whereas in reality, in the ground frame, with respect to the stationary ground, B has moved much more. It has moved 250 meters. But during that time, you have also moved as the observer A. You have also moved 200 meters. So that's why. So that is the advantage of solving the problem in the relative motion method, because then we don't have to make this kind of a calculation and observe the displacement of all three and all that. Okay. So this is precisely the reason why we study the equations of relative motion, so that when we are looking at motion of two moving objects, we don't have to individually solve their motion. We can reduce it to the motion of one object with respect to another by moving our reference frame from the ground. Here our reference frame is on the ground, but in the earlier method of solving, our reference frame was inside the car. So it was a moving frame. So then what happened is, for us, one of the objects became stationary because our reference frame was attached to that, and we solved the motion of the other two relative to that. So that was advantageous, because then for us, we didn't have to track the motion of A. We just had to track the motion of B and C with respect to A. So that's why it's a more efficient and easier way of solving the problem compared to this method. Okay. So just make a note of this, and hope you understood this properly. Okay, so people hope you understood, the difference between this picture and the earlier picture that we solved. That was with respect to, yeah, Bhumik, I will not scroll for the question now. You had enough time to write down the question. Okay, so don't unnecessarily disturb the whole class by instructing me, go here, go there, do this, do that. I will send you the PDF later. You can see it up and down as many times as you like. Just concentrate on what I'm showing in this diagram over here. All the information that you require is there in the diagram. E's initial velocity is shown, B's velocity is shown, C's velocity is shown. The initial distances are shown 50 meters and 50 meters. And we are just solving what is happening from 0 to T2, which is 10 seconds. So just concentrate on this part. Okay. Are the calculations clear in this diagram, people? These three calculations, the displacement of A, the displacement of B, and the displacement of C as seen from the ground plane. Are these calculations clear? Because velocity of A you can see is 20 meters per second in the positive direction. So in 10 seconds, the displacement will become plus 200. So A will reach from this point A to this point A prime over here. And that point should be how much ahead? It should be 200 meters ahead. Similarly, B's velocity you can see is 25 in the positive direction. So the displacement should become plus 25 meters per second into 10 seconds. So plus 250 meters. So B would have reached from here to 250 meters ahead. So the moment you see this, that this is 200 and this is 250, you realize that yes, what we have seen earlier was correct. That at 10 seconds, they're going to be alongside. Because A started 50 meters ahead of B, but then B has traveled 50 meters extra in 10 seconds. Now, similarly, C's velocity is how much? It is actually minus 10 meters per second when we write with the algebraic sign. Therefore, the displacement of C, which is Vc into time, with the proper sign, will be minus 10 meters per second into 10 seconds, which is minus 100 meters. So that's why C is going from here in the opposite direction to this point C prime. And it just so happens that it comes over here because that's exactly 100 meters. So now at your new time T prime, what is happening? Or your new time 10 seconds, what is happening? A is located here, B is located here. So B is about to cross A. Whereas what about C? C is right behind over here. So where is C? It is at a distance of this plus this, and that total distance is how much? 250 meters. Hence we got this. That at 10 seconds, A and B are alongside each other. So B is about to overtake A, but C is behind them both, now at a distance of 250 meters. And this is exactly the same data that we got in the other method of solving using relative motion. Then it takes 10 seconds for B to overtake A or to come alongside A, and during those 10 seconds, the distance between C and A has changed to 250 meters. Okay, people. So hope this is clear to all of you. Now you will get to check your problem solving ability in this type of question through the next example, which is a slightly trickier version of this question. Okay, so this is now we are coming closer to actual the JEE type of logic you have to use in exams like JEE, the type of logic you have to use, that kind of thing. So here we are having two trains, let's say, which are moving on straight tracks, and they are initially like this. So now that thing you were saying that if the length of the car is given, how to deal with that? So that you'll have to think about in this question. So instead of the car itself here, we are taking it to be a bigger object like a train. Okay, so the length becomes pretty much more significant. Okay. So these are two trains which are like this, and they are traveling on opposite paths along straight tracks. Okay, so let's okay, so let's just take some nice reference names. Since we can't travel right now, so let's just live vicariously. So this is, let's say, Gitanjali Express. This is a train that I used to travel a lot in my student days, because I used to travel from Mumbai to Kolkata by Gitanjali. Nearly takes 2 days, maybe 1.5 to 2 days to reach. So Gitanjali Express, let's say, has a length L1 and is traveling with a uniform velocity in this direction of V1. And from the other side, let's say, Bombay Mail, it was another train on the same line actually, is coming back. So it's coming in the opposite direction, and its velocity is V2 and its length is L2. So suppose given to us that the length of the Gitanjali Mail train is, let's say, whatever, it is some 100 meters, and the length of Bombay Mail is slightly greater, let's say it's 120 meters, and they are traveling at uniform velocities. Of, see, V1 equal to 72 kilometers per hour and V2 equal to 54 kilometers per hour, as shown along straight and parallel tracks. Okay. So now suppose at the instant when we start our stopwatch, this front to front distance between them is some value capital D. So this is a picture at t equal to 0. I'll show you the diagram again, don't worry. So at t equal to 0, okay, that distance d between them was, let us say, 50 meters. So find the time taken for them to cross each other completely. And their individual displacements during this time. So whatever this time interval is when they are crossing each other, during that much time, what are their individual displacements? See, so just note down the data of the question and the diagram properly first, then I'll take you to the 2 questions below. So these were 2 very legendary trains, Gitanjali Express and Bombay Mail. Of course, it's been many years since, like nowadays people travel by flights, so that whole thing of a long train journey has gone out of fashion. But during my student time, we used to all travel by train mostly, and we could finish a couple of books by the time we reached across the country and all that. So These are the individual trains. So you can also start by calculating the relative velocity. So just make a note of this diagram first with the data over here, then I'll take you to the questions below. Okay. So the questions below are this. Now be mindful of the fact that the units are different over here. The distances are given to you in meters, whereas the speeds are given in kilometers per hour. So you will have to adjust and get them down to the same system of units before you start your calculations. So if you remember the question we did last time of that long, trailer truck being overtaken by a car, how we had solved that one by relative motion. You can think of a similar kind of approach over here. Okay, so anybody got the answer so far, people? Yeah, Adinath, you got the correct answer. Dhruv, unfortunately, you have to check your answer. It's not correct. Yes, Bhagyashri, correct. Yeah, Dhruv, now it is correct. Now the value of time was calculated, that is correct. So have you people done this by relative motion method? Good. Correct. Good, better. Very good. That's correct. Okay, so let's look at the full solution once again. Okay, so let me say that suppose my observer was sitting inside Gitanjali Express. So Bombay Mail would appear to come with a relative velocity like this. This is what would happen. So if you look at the motion of Bombay Mail with respect to Gitanjali Express. So the relative velocity of Bombay Mail with respect to Gitanjali Express would be the individual velocity of Bombay Mail minus the individual velocity of Gitanjali Express. So that would work out to be Bombay Mail's velocity was in the negative direction and it was in meters per second, 15 meters per second. So better we put this inside the bracket. Whereas Gitanjali Express's velocity was in the positive direction and 20 meters per second. That's 72 kilometers per hour is 20 meters per second, and 54 kilometers per hour is 15 meters per second. So making use of that. So it is minus 35 meters per second. This is the velocity of the oncoming train as seen by an observer inside Gitanjali Express. So to an observer inside Gitanjali Express, it looks like Bombay Mail is coming at a velocity of 35 meters per second towards him. And this is where Bombay Mail is at t equal to 0, where this distance is capital D. Of course, this length is our L2 and this length was L1. Okay. Now suppose they've overtaken, they've crossed each other completely after a certain amount of time. So at that instant of time, it looked like with respect to this guy, this one has reached somewhere here. This distance. So it See, this is where my Bombay mail is as seen by Gitanjali Express, but at time t equal to some time that we are trying to calculate. And this is when they have exactly crossed each other. So you can see that the displacement of yeah, people, am I audible now? Yeah, I think it's okay now, right? Okay. So yes, good. Yeah, just my internet connection got interrupted and I got locked out from both the sources. Anyway, so now things are normal again. So going back here, so in the reference frame of Gitanjali Express, okay, so this is the the velocity of Bombay Mail relative to Gitanjali Express, okay, and in time 0 to t, okay, the displacement of Gitanjali Express, or rather Bombay Mail with respect to Gitanjali Express, that relative displacement, that you can see in the diagram was nothing but minus of 270 meters. Because going back to the diagram, you can see it was this. So this is going to work out to be L2 was 120 meters. The initial distance between the engines was 50 meters, and L1 was 100 meters. So it was equal to 270 meters. But the direction is backwards. So that's why this quantity here, the displacement of this train with respect to Gitanjali Express, should become with proper sign minus of 270 meters. So basically the engine of Bombay Mail to you, it looks like the engine was 50 meters ahead of you initially, and now it's gone to a point of this much behind. That is, you will see that is 220 meters behind. So it has gone from 50 meters ahead to 220 meters behind. So it's totally traveled 270 meters backwards. So there you are. By this ratio now you can calculate the time. So you got the relative velocity and you got this. So the time t should be equal to nothing but displacement divided by time. Sorry, divided by velocity. So magnitude wise, this becomes 270 by 35, okay, which will work out to be 54 by 7 or approximately 7 point something 17 seconds. So this is the first part. This is, you have to calculate the time from this, right? And once you got the time, you can calculate the individual displacements very easily. So I'll just minimize this for all of you to go through the whole thing. So this diagram here, it is explaining the motion of Bombay Mill as seen by an observer inside Gitanjali Express. So it is relative to Gitanjali Express. So our observer is inside Gitanjali Express. Okay, so this is done. Yeah, Dhruv, your question, just a moment. Yeah, Dhruv, actually when I got logged out, I missed that message you are probably referring to. So which answer you were asking? Can you send it to me again? So from this we have got the time taken. Now we have to find the individual displacements. So for the individual displacements with respect to ground, with respect to the stationary ground frame, all we have to do is we have to understand the displacement of, yeah, just multiply velocity with time. Okay. This will be velocity of Gitanjali Express into the time. So that velocity was 20 meters per second into the time was 54 by 7. So this will become your displacement in meters, and this is obviously in the forward direction. The other one will be in the backward direction. So approximately this will be 154.4 meters. Whereas during that same time, if you look at the displacement of Bombay Mill, it will be minus of 15 meters per second into that time, 54 by 4. So with the proper sign, the displacement will be a negative quantity, and with the proper sign, minus sign, it will become or 115.8. So now you can verify this data to understand how the relative displacement is 270 also. So now you can also check this thing, that this tallies with this value. This value should tally with respect to this one and this one. So let's understand that. So finally, seeing that the displacement of Gitanjali Express with respect to ground is positive of 20 into 54 by 7 meters. Just giving it in fractional form. The displacement of Bombay Mill is in the opposite direction. So minus of 15 into 54 by 7. So by the laws of relative motion, remember we had discussed about relative displacement also. What was the definition of relative displacement? the displacement of one object with respect to the other is the difference of the two. So, sorry, displacement of Bombay Mail relative to Gitanjali Express, as seen over here, is going to be this minus this. So it is minus 15 into 54 by 7 minus of plus 20 into 54 by 7. So taking the minus sign common and taking 54 by 7 common in the calculation. So you have 15 plus 20. So that is minus 54 into 35 by 7. So that will become minus 270, which is the expected answer. It should be minus 270 meters because that is what we had also seen from the logical point of view, that it is L1 plus L2 plus D in the negative direction. So this answer is now justified from the earlier equation that we written from the relative motion picture here. See, here we had written this because in the diagram it was this. In the diagram it was this amount here. So this here is agreeing with what we are getting by solving the ground frame also. So that also, that verifies that we have not made any calculation mistake and things also. Okay, so just add this point over here, finally over here. Okay, so hope this question is clear by this method over here. Now we come to the last part of relative motion, which is we'll understand how to deal with relative motion when there is acceleration involved, that is velocities are not uniform. So this is our next theory point. Relative motion. Obviously, we are still in 1D, one dimension. For accelerated particles or bodies or whatever. So how do we deal with that? So it is the same chain of logic that we will see applied over here. So I'll just remind you of the chain of logic that we discussed, that it started with relative position. We've seen relative position of one body with respect to another was the position of the first body minus the position of the second body. So from this we had seen that relative displacement S. Now displacement is always change in position. So it is delta x. So it is nothing but change in xb minus x. Because you're just incorporating this definition into now this definition, that if position, if displacement is change in position, then relative displacement is change in relative position. And relative position itself is the difference of xb minus x. So further it becomes delta xb minus delta x. And by definition, this is the individual displacement of B, and this is the individual displacement of B. So that's how we got the definition of relative displacement as the difference of these, which incidentally we just used in the above questions also in this question. Okay. Now, similarly from this, we got the definition of relative velocity. we talk about relative velocity. So that velocity of some object B with respect to another object, it will be rate of change of displacement of B. I mean relative displacement of B with respect to A. It will be rate of change in terms of time for that. Okay? So further, this will become change in relative displacement, which is SB minus SA divided by change in time. So further, that becomes how much? It becomes delta SB by delta T minus delta SA by delta. Here we are using a different thing. We are using the distributive property of division. So we are using something like this, that A minus B upon C, then written as A by C minus B by C. That kind of thing we are using. Now further, by definition, we saw that this quantity is nothing but the individual velocity of B, and this quantity was the individual velocity of T. So that is how we got the definition, that relative velocity of B with respect to A becomes this. And this is what we've been using till now. Because of this equation, only two things approaching each other from opposite directions, their relative velocity actually becomes the sum of the magnitudes. Whereas two things going in the same direction, their relative velocity becomes the difference. That thing. Now let us carry this definition forward for relative acceleration. So relative acceleration will define like this. Acceleration of body B or particle B with respect to A. How will we define that? So we remember from 1D motion, what was the definition of acceleration? Acceleration was rate of change of velocity. Okay. So here relative acceleration will become rate of change of relative velocity with respect to time. So as a definition, this becomes like this. Relative acceleration equals to the rate of change of relative velocity. Instead of just velocity, the rate of change of relative velocity. So if here we are calculating relative acceleration of B with respect to A. So here also we have to define it in terms of relative velocity of B with respect to A. So this is what this side is, and this is what. So this is the definition. This is the definition. So just make a quick note of this first, then we'll see, we'll reduce this further. Okay, now let's see how we can reduce it using the definition. So since velocity of B with respect to A, we've already seen is velocity of E minus velocity of E. Therefore, acceleration, which is the rate of change of this quantity with respect to time, will actually become rate of change of the difference of the individual velocities with respect to time. So now change in B minus change in A can be written as change in B minus change in A divided by delta T, and further this can be written as delta VB divided by delta T minus delta V divided by delta T. And now by definition from your 1D kinematics, rate of change of velocity of any particle is nothing but its individual acceleration as seen in the ground. So this is the individual acceleration of B minus the individual acceleration of B, and that is what becomes your left hand side, which is the acceleration of B with respect to B. You see, you have an entire series of formulae which are all symmetrical. So you don't really need to memorize them separately. You just understand them logically like this. That position of B with respect to A was position of B minus position of B. Now apply delta on both sides. So change in relative position becomes relative displacement. And on this side it becomes change in XB minus change in XA. It becomes SA minus SB. Okay. Then divide by time on both sides. So it becomes velocity of B with respect to E. Becomes velocity of B minus velocity of E. Just a correction here. This should be B minus E. Right? So in the first equation, you just apply the quantity that change in left hand side is equal to change in right hand side. You get this equation. And then you apply on this equation, you apply rate of change. So rate of change of left hand side is equal to rate of change of right hand side. So you get this. And then again, you once more apply rate of change. So you get this. That rate of change of relative velocity is acceleration, relative acceleration. So that will become rate of change of this whole thing. So that will become rate of change of VB. That is nothing but acceleration of V minus rate of change of. So that is okay. So this now becomes our working formula for relative acceleration. While the definition was above, this now becomes our working formula. For relative acceleration. Okay, so we will see this with examples next, but just note this down. Okay, so hope this is clear, people. Understood the definition of relative acceleration from this. So we have an entire symmetrical series of formulae like this. So this will be like this. So let's just understand this with an example. So suppose we have a bus and a car or a trolley or something. Now this is moving with an acceleration a1 of 2 meters per second square, and this is moving with an acceleration a2 of 6 meters per second square. Okay. So the bus and car are moving along a straight path at uniform accelerations. A1 and A2 respectively, as shown. Also, at t equal to 0, which is this instant when they are shown like this. At t equal to 0, their velocities are v1 equal to 20 meters per second and v2 equal to 10 meters per second respectively. Now what we have to do here is, first of all, find the acceleration of the car with respect to the truck. The acceleration of the car relative to, sorry, the bus, whatever. And then secondly, find the velocity of the car with respect to the bus as a function of time. And from that, you have to comment estimate how the distance between them changes with time. That is, does it increase or decrease with time, etc. So this is what we have to do. So I'm just minimizing the question so that you can see the whole thing and calculate this. Okay. So certain parts of it are directly formula based, you can directly answer them. But the last part is the interesting thing, so think carefully about how you will get that. Yeah, Bhaumik, your answer for the first part is correct. But second part, you have to be a little careful. We are talking about velocity of the car with respect to the bus, not at t equal to 0, but as a function of time. Now they are accelerated bodies, na? That means the relative velocity will be changing with time. So you can't say it's so many meters per second. It must be changing with time. It must be a function of time. You're getting my point? Had A1 and A2 being 0, then okay, we could have said relative velocity is just going to be that much only. It's going to be minus 10, it's going to be constant. But here there is relative acceleration. Na? So that means the velocity is going to change with time. Okay, so must have got the first part, all of you. This should come out plus 4 meters per second square. The relative acceleration of the car as seen by the this thing, bus. Now, what about the velocity as a function of time? So I'll just give you the answer. Then we'll discuss about the solution. Okay. So the answer to this will be that it will be minus 10 plus 4t as a function of time. So this is what is going to finally give us the idea that the distance first decreases and then eventually increases. It's a very curious thing how that happens. So we'll understand this logic carefully. But first try to figure this out yourself. There are multiple ways in which you can come to this answer. Okay? The second one's answer. The acceleration of the car as seen by the bus is equal to plus 4. This is very simple because they're uniform acceleration, so we just subtract the two. But from that, this second part's answer, there are multiple ways in which you can calculate this. Okay, so just try this out. Okay, so I'll give you a hint. You can do something like this. You can have two options. One is you can calculate velocity of the car as a function of time. And similarly, velocity of the bus as a function of time. And then from that, calculate the velocity of the car with respect to the bus. Or you can also do this. You have the acceleration of the car in the relative phase. And you have the initial velocity of the car relative. You know the acceleration of the car with respect to the bus. And you also know the initial velocity of the car with respect to the bus. You can also use kinematics. So there are two different options by which you can go. Now, method one is this. You can use this kind of a method. Okay. And method two is this. And you can use this data. By either thing, you will see it will come out to be like this. Okay, so let me, so first of all, does the answer make sense that the distance is first decreasing and then increasing? Because see, let's try to understand this without getting into calculations and all first. Okay, let's just try to track the motion first. So if let us say I'm just treating the bus like a particle here. Now at t equal to 0, it has a velocity of 20 meters per second. And of course, it has an acceleration of 2 meters per second square. And let's say the car is somewhere over here. And the car had a velocity initially at t equal to 0 of 10 meters per second and an acceleration of 6 meters per second square. So at this moment, if you see, what is the relative velocity? The initial relative velocity of the car with respect to the bus, okay, at t equal to 0. It is the initial velocity of the car minus the initial velocity of the bus. So that will come out to be minus 10 meters per second. So that means initially at this moment, the car appears to be coming closer, because it has a backward relative velocity to the bus at the rate of 10 meters per second. This is what it means, that for the person sitting inside the bus, it looks like the car is coming towards him at 10 meters per second. This is what this looks like. Okay. Now let's track this same thing after a few seconds. Okay. So let's say let's say we're looking at the same thing at, let us say, t equal to 5 seconds. So at t equal to 5 seconds, the velocity of the bus has become the initial velocity of the bus plus acceleration of the bus into time. So it has become 20 plus 2 into 5. So it has become 30 meters per second. This is what the velocity of the bus has now become. But at the same time, what about the velocity of the car? It has become the initial velocity of the car plus acceleration of the car into time. So the initial velocity of the car was 10, but the acceleration was 6. So it has actually become 40 meters per second. So very interestingly, you can see that now at this instant, the velocity of the car with respect to the bus has changed to plus 10. So basically at t equal to 5 seconds, the car appears to be moving away from the bus. At 10 meters per second. So I'll just a moment. So this is happening at t equal to 5 seconds. So if you put together this information with what we saw at t equal to 0, so you'll understand something like this, that if at t equal to 0, the situation was something like this. The bus was here and the car was somewhere here. So at that moment, to the observer inside the bus, it looked like the car had a velocity like this. This was the velocity of the car with respect to the bus. It was minus 10 meters per second, but coming, so that's why coming closer. But by the time it is now 10 seconds, 5 seconds, So at t equal to 5 seconds, let's say the bus is now reached somewhere here. The car is, let's say, reached somewhere over here. But now to the observer inside the bus, the relative velocity of the car has changed direction. It has become the other way. It has become plus 10 meters per second. So it has become like this. Why? Because when you see from the ground frame point of view, what was happening at t equal to 0, the velocity of the bus was plus 20 and the velocity of the car was plus 10. Okay. But by the time you came to t equal to 5 seconds, in the ground frame, the velocity of the bus it increased, but only from 20 to 30, whereas the velocity of the car increased very much more dramatically. It increased from 10 all the way to 40. Okay. So by the time this is happening now, you can see that the car is pulling away from the bus, whereas initially the bus was gaining on the car. Okay. So that is why this is what is happening. Yeah, I cannot quite understand your message, Yuvraj. Maybe some typing mistake. Okay. So this is giving you the evidence of what I've given as the answer in the third part. Okay, so here at t equal to 0, you can say the bus is gaining on the car. It's coming closer. But by the time this happens, now the car is pulling away from the bus. So that is why you can see that the distance initially decreases and eventually increases. Now this is just like I've got this by just using a little bit of logic without too much of equations and all that. Now we can also support all this with more formal equations and by even drawing a graph and all that. But since the question was just asking you to comment what is happening in terms of the behavior of the relationship between them. So this is enough actually to understand that. Okay. So I'll just take you to this understanding. So this is what was happening initially at t equal to 0, and just below that I'll show you what's happening at time. I've just taken an arbitrary time of 5 seconds, but that time interval was enough to show that the behavior of the relative velocity has changed. It has gone from the car moving towards the bus to the car moving away from the bus. So that is why the behavior of the distance has changed from a distance which was initially decreasing to a distance which after some time starts increasing again. Okay. So just make sure you understand this first, this part, then I'll take you to the part below. This is at t equal to 0. So at that initial moment, this is what this observer sees. To him, it looks like that the car is coming towards him at 10 meters per second. But move ahead, fast forward ahead 5 seconds and come to an instant like this at t equal to 5 seconds. And the whole situation has changed to this. This is what is happening at t equal to 5 seconds. Okay, the velocity of the bus is increased from 20 to 30. But the velocity of the car is increased much more from 10 to 40. So therefore, now at this moment, what is happening to the bus? It is looking like the car is actually moving away. This with the relative velocity of 10 meters. This is what is happening at 5 seconds. If you compare the two pictures together now, you get the last diagram over here. This is what was happening initially at t equal to 0. And now this is happening at another instant of time 5 seconds. Now, when we solve this mathematically, you will see that we will come back to what we discussed 2 or 3 lectures back, and that is the graph of quadratic functions. And the graph of that quadratic function will help us understand the behavior of this distance, why it is first decreasing and then increasing. All right. So people, now let's understand second and third part by mathematics. This was just a sort of intuitive way of understanding it. Yeah, Bhumi, I'll give you some tips for the exam, don't worry. So now the second part, we wanted to find the velocity of the car with respect to the bus as a function of time. So for this, we had one method which was solve in ground frame for the velocity of the car and the velocity of the bus, and then apply relative velocity formula. Okay. So for that, you'll see that for the car, or rather, let's start with the bus. For the bus, the initial velocity was plus 20 meters per second, and the uniform acceleration was plus 2 meters per second square. This was uniform. So for the bus, our velocity as a function of time will just become u plus at. So this. So it's just becoming 20 plus 2t. This is the velocity of the bus in meters per second at some time t. Okay. Now repeat this exercise for the car. Okay. So for the car, what was happening? The initial velocity with proper sign was plus 10. They were both going in the positive direction, but the acceleration of the car was plus 6 meters per second square. So at a time t, the velocity of the car will just become u plus at. So the velocity of the car as a function of time is becoming 10 plus 6t in meters per second. So now I've got my objective. I've got the velocity of the car as a function of time. I've got the velocity of the bus at a time t. Okay. So now you can see that at some time t, the velocity of the car with respect to the bus will become the velocity of the car minus the velocity of the bus. So that is 10 plus 60 minus from above 20 plus 2t. So as a function, it is becoming like this. It is becoming 4t minus 10. Becoming like this. This should become our answer in meters per second at time. So therefore, you can see that at t equal to 0, your initial is minus 10, and that is what we had seen in that example also. At t equal to 5, you can check what was correct by this formula also. The velocity of the car with respect to the bus will just become 20 minus 10, so that will become plus 10. So this also agrees with that, the arbitrary calculation we had done earlier for 0 and 5 seconds. It agrees with that. Okay. So let me minimize this and just go through this once first. So there's nothing extraordinary in this. We are just using the simple equation of motion with uniform acceleration. The velocity becomes u plus at. So individually apply that to the bus once and apply that to the car once. Okay. So from this, you're getting velocity of the bus as a function of time. From this, you are getting the velocity of the car as a function of time, and then from that you calculate the velocity velocity of the car with respect to the bus. That's okay. Right, so fairly obvious and clear. Now, alternately, the second method we can apply here, like this. We can solve the relative velocity of the car in the bus's frame. So here then what we're doing is, from the beginning our observer is inside the bus and he's observing the car. So we're trying to track this as a function of time. Okay. So for that we know that the initial velocity of the car with respect to the bus is the initial velocity of the car minus initial velocity of the bus. So that was minus 10 meters per second, because we know the initial velocities were like that. And the acceleration of the car with respect to the bus, which is acceleration of the car minus acceleration of the bus. So that we know was how much? That was plus 4 meters per second. So we now know this. And we know that this acceleration is uniform. So we just use the equation of motion for uniform acceleration. So we just use that at time t, the velocity of the car with respect to the bus will become u plus e. But which u? The relative one. And which acceleration? The relative one. This. So you are using a standard equation of motion, v is equal to u plus at, but instead of using it in the ground frame, you are using it in the bus's frame. You are using it for the observer who is inside the bus and is observing the car. So he is seeing the car's initial velocity is minus 10, but his acceleration is plus 4. So according to him, this should be the velocity. Very simple. And this is the same answer that we got earlier. So again, you see the advantage of using relative motion. Now, you have to worry about less number of things when you are directly using relative motion equations. Yes, exactly the point. The second is much easier, and that too we'll see how we apply this when we're doing the third part of the question also. So you realize how much more advantageous relative motion is as a method. So this part is clear, people. Now, if you followed this, then it will be very easy to understand what's happening in the third part. Just continue with this, but think about the displacement. So for the third part, let us solve for this quantity, the displacement of the car with respect to the bus. Relative to the bus. So our observer is inside the bus. And now the car, in his frame, how it should displace. That thing we want to calculate. If it reaches from here to here after some time. So this is the displacement of the car with respect to the bus. So for that, to calculate this, you can see that the initial velocity of the car with respect to the bus, we had just seen, was minus 10, and the acceleration was plus 4. So make use of that. So make use of this fact that this was minus 10 meters per second. We've seen this before. And the acceleration of the car with respect to the bus was plus 4 meters per second square. and it's a uniform acceleration. So now instead of using the v is equal to u plus at equation, use the s is equal to ut plus half at square. But instead of in the ground frame, use it in the relative frame. So it is displacement of the car with respect to the bus is this. Okay. So this will give us the relation that displacement of the car with respect to the bus is minus 10t plus 2t square. And this is where now our understanding of quadratic graphs will help us. Okay. So just come up to this step, and next we'll plot the graph of this displacement versus time, and from that we'll understand why the car is first coming closer and then going further away. Why the distance is first decreasing and then increasing. It's going to be very evident the moment we think about the graph of this relation. So are you clear up to this step? Okay. Okay, so now, just a moment. Just hang on a second, people. Reshare that. Okay. So we should be good to go now. Right. Now, in this, what we'll do now is we'll plot the graph of relative displacement versus time. So this is which type of a graph? It's a quadratic graph. This relative displacement is 2t square minus 10t. So you can take 2t as a common factor, t minus 5. Okay. So you can see that this is a quadratic equation. So the graph will be a parabolic graph. Okay. If you remember about your parabolic graphs, y is equal to ax square plus bx plus c. Now what happens when a is positive? When a is positive, the shape of the graph is like this. It's a parabola opening upwards, and wherever it cuts the x-axis, those are my roots. Okay, Tanish, I'll just finish in. So the last part you can check out from the video later. Okay, Tanish. So these are the roots, alpha and beta. Okay. So in this case, what is happening? It's a quadratic graph with the value of e as 2. That is the coefficient of the square term is positive first. Okay. And the other thing is that the roots are 0 and 5. So when we plot this graph of displacement versus time, so relative displacement of the car with respect to the bus versus time in seconds, okay, we'll see that one root is 0 and the other root is 5 seconds. Okay. And in between the graph should be like this. It should be going like this. So we won't plot the negative time side. We'll only plot the positive time side. Okay. So it's looking something like this. Okay. The mathematical graph would have been like this, but here negative time doesn't make sense. So we can see that the displacement is first negative for some time, and then it starts becoming positive. So you can see here that the displacement is negative from 0 to 5 seconds, and then it becomes positive for time greater than 5 seconds. So when the displacement is negative, imagine what is happening to the car. It's coming closer now. This is the bus and this is the car. When the relative displacement is negative, that means the car is coming like this. So the distance is decreasing. And when the relative displacement becomes positive, it's again increasing. So this explains why that happens. Okay, so because it is first negative and then positive, you can see that the distance decreases first and then increases. So that is the full logic. Okay. So I'll just minimize this and read this to you. Okay, people, so that will be all for today's lecture. And about your test coming up on Sunday, don't worry, it's a very simple test. You will have only multiple choice questions with single options correct. And mostly the new thing you have to prepare for that is the vertical motion type of problem that we've discussed in last lecture and the one before that. So if you go back to 2 lectures before today's lectures, you will see example problems of vertical motion and those kind of situations where you projected an object vertically upwards. So its height is increasing and then eventually it's coming down, and how to calculate the maximum height, the total time taken, the distance covered and things like that, using the value of acceleration due to gravity, okay, that kind of thing. And the basic part of relative motion, that is relative motion without acceleration. Today we have discussed in the last part of the lecture relative motion with acceleration. So that you can exclude for your preparation for the test coming up on Sunday. That will come in the next test after that. But before that, what we've done, those type of problems whether 2 trains were approaching each other or one car was overtaking a bus or something like that, those kind of relative motion type of questions where there is relative motion at uniform velocity. So make sure you revise those and make sure you revise the problems of vertical motion. If you do that much, it will be more than enough for your preparation for the test. Okay. Yeah, I'll scroll up for you. Okay. I'm going to send the whole file anyway. So this one. Okay, people. So that's it for today's lecture. God bless and stay safe during the lockdown. Yeah, Bhavik, I will scroll down also. Some people want me to scroll up, some want me to scroll down. So, yeah, and to answer your question, Bhavik, there will be negative marking. So the marking scheme will be, there will be 30 questions in physics, 30 in maths and 30 in chemistry. And each correct answer will fetch you +4 marks. Each wrong answer will fetch you -1. So +4 for correct answer, -1 for wrong answer, and 0 if you don't attempt the question. So only attempt the question if you're sure about the answer. Because, oh yeah, biology also, correct, sorry, my mistake. PCB. Okay. So here we are plotting this kind of graph. This kind of parabolic graph, where the roots are 5 and 0. So in fact, it will reach the minima also. We discussed last time the vertex point. Vertex कहाँ पे होगा? Vertex में यहाँ पे time axis है instead of x axis है. So in the vertex, the value of time will be 0 plus 5 by 2 or 2.5. So that is the explanation for why the displacement is first becoming negative. No? So as it's becoming negative, it's coming closer, and then eventually the displacement is positive. So then the distance starts increasing. Okay, guys. So that's it for today's lecture.